All right, so if we're going to be constructing the molecular orbital diagram of methane, we need to look at all of the why did I put A prime? I was supposed to.
Oh, it's supposed to be A1.
Yeah, there's supposed to be A1. We were showing why you can't just force a well, you can't just force a p orbital in there.
I wrote it as A1, so you must have at least said it.
Yeah, I said it as A1. I just wrote it as A. I don't know, but anyway, we got to start looking through and constructing the molecular orbital diagram. So you notice that our primary structures are going to be A1, T2, A1 star, and T2 star. Okay. So let's think about this. We know that the bonding has to be lower in energy. Which one do you think is the lowest, the A1 or the T2?
The A1.
The A1. So what we're going to start with, we're going to have our A1, then our T2 level, going to be there. Then what do we think? What do we think next? T2 star or A1 star? If we think about how we've done molecular orbitals in the past, even all the way back to Gen Chem. So it's basically look at them, and which one do you think is going to have more repulsion? That's going to be the higher in energy.
Have more repulsion?
Yeah, so
maybe A1 star?
Yeah, so A1 star is going to have a fourfold repulsion upon, at the center. Whereas the T2 star, you're going to get twofold repulsion at each end of the p orbital. So the T2 star will be a little lower in energy. So we'll just put that here. Our A1 star up there. A1, T2, T2 antibonding, A1 antibonding. And then we think about what we have as far as our orbitals, our atomic orbitals that contribute. So let's see. We know that our carbon is going to give a 2s and then the px, py, pz. Okay, so the 2s is going to be the A1 for the carbon. It's going to go somewhere kind of like right up in here. And then our px, py, pz be slightly higher in energy. Okay, and then on the other side, all right, so our ligand groups of course are going to match in symmetry. So we have our T2s up here and our A1 there. And then we start saying, well, where does everything go? All right, well, your T2s are going to combine, form T2s. And then, of course, your A1s are going to combine to take care of all the A1 symmetry molecular orbitals. So honestly, your methane is really only this complex.
That's basically what I did, but I had different energies for the atomic orbitals.
Yeah, well, the thing is, some of these you can look up and get them, but it just, a lot of this stuff is getting used to what these look like. Okay. So then if we take a look here, this is pretty much the structure of our molecular orbitals. And so of course you see that you can see the difference between the A1, all of that, all of the bonding to the A1 star. And then you can see these various T2 orbitals. Mm-hmm. So they come out looking a little wonky, but you know.
That's okay.
All right, now, one that's a good deal more complex, carbon dioxide. You wouldn't think of carbon dioxide as being extraordinarily complex. But the first thing we want to say is like, well, we've been using the character table and characters to kind of figure this out right now. Maybe there's a more intuitive way to do this because that D infinity H table is not a nice one.
Yeah, that sucks.
Now, as we're going through, so remember your sigma is going to be your completely symmetric with some phase changing between your plus ones and minus ones. Your pi's are going to have one nodal plane. Your deltas will have two nodal planes. There's no phi's on here because that's just more, that's more complex symmetry. So that's what these are going to mean. And then, of course, your all of your ungarage garage pluses and minuses. But there was a slide on what all that means, but we're just going to kind of leave that be. Okay. So now the book doesn't do this. The book sticks to solely like S and P orbitals, which is valid for constructing a molecular orbital system. What I wanted to do was I wanted to say, well, actually we know that our carbon and our oxygens are both going to hybridize. So I've actually tried to include those in the molecular orbital structure so we can kind of figure out where they're going to go, because of course we don't want to just, I really don't like when we teach people a certain kind of theory and then we go and say, yeah, now just forget all that.
Yeah.
It's like, at the end of the day, and someone might argue like, oh, using the hybrid orbitals is inappropriate. It's like, dude, if you really want to talk about inappropriate, this is all a scheme to try to explain what's actually happening.
Yeah.
Whereas we could just straight do the quantum mechanics and calculate the molecular orbitals. So we could either quibble about the scheme, or we could just say, well, if we don't want to argue about that, let's just drop all of these and just do the quantum mechanics. But then you get most people going, I don't want to do quantum mechanics. All right, well then let's not argue over the scheme.
Yeah, just do this. This is fine.
Okay. So remember that our oxygens, of course, are going to have lone pairs. And so our carbon will be sp hybridized. Each oxygen will be sp2. Okay. So let's kind of see what this is going to look like. So you're going to notice as we go through, this is too complex. So our molecular orbitals, we're not going to be labeling them as like sigma G plus, sigma G minus. This is going to be a structure of like pi G's, pi U's, sigma G's, sigma U's. Because I mean, we could go through and figure all that out, but man, that's going to be a lot of complex work. And the accepted way to do CO2 is just like, let's just do pi, pi U's, pi G's, sigma U's, sigma G's. We'll just do that. Okay, so our carbon is going to have So it's going to have that, and then it's going to have its p orbitals. So we need to start by saying one of these is ungerad, one is gerad. What do you think? Do you remember what those are? They're symmetric and anti-symmetric under what operation?
Is it it's the plane?
Not plane.
Not the plane? Is it the primary axis?
It's the one we've barely used so far.
The one we barely used.
Gerad and ungerad are symmetric and anti-symmetric under.
Is this the sigma D?
It's,
what?
No, it's under inversion.
Under
So that makes
okay.
this one gerad.
Yeah.
And that one ungerad.
Okay.
Okay, so that's what we're working with. Those are our basic symmetries, gerad and ungerad symmetry. Okay. Now, let's kind of start talking about the various ligand group orbitals. Okay. Okay, so your oxygens, the first thing it can do is we can get these s orbitals. And then, of course, there's our other set of s orbitals. What do you think happens with this second set?
They're just opposite phases.
Yep, so these are our s orbitals. And now, what kind of bonding do you think these are going to form?
This is sigma bonds.
Mm-hmm. So this will be sigma U. That will be a sigma G. Now, we know that our oxygens also form these sp2 orbitals. So let's say yeah, they kind of look like p orbitals. Kind of, but not really. But so I guess if you really want to do this properly, you say, well, then I have this smaller lobe on the back, and over here. Okay, and these are also okay. So maybe we'll take. Get that one. Now I'm going to try to draw. No, I don't want to play around with which one's bigger, which one's smaller. Just know that that's what these do. Okay. Okay, so then this one. We'll have this alternate phase that we know we have to have. So this is the same. These are also going to be sp2s. All right, so these, of course, the way they're pointed, we know that the sp2s form sigma bonds. Okay, so sigma G. Hang on, no. That one's U. And that was G. Because if you invert those, You see that on the top when the phases change and on the bottom when they stay the same. And then let's also keep in mind what our carbon did. So what we have 2px, 2py, and sp. So even though that still looks like it's a p orbital in there, it's actually our carbon's sp hybridized orbital. Right. Okay. So now there's a couple of other options with the ligand groups. And so keep in mind that the oxygens are going to use each one's going to use two of its p orbitals, and it's going to leave for hybridizing, and then it's going to leave one of its p orbitals for pi bonding. But we don't really know. We know that one of those double bonds is going to be in and out of the plane, one is going to be above and below the plane. So we have to allot for both possibilities. And so our next ligand group let's try to imagine that one's on its side. Okay, both of these are going to be pi U ligand groups. Okay.
And will the phases go the same direction each time?
We'll do that in just a second. So for these two, these are both pi U. If you invert, you can see you're going to switch phases. And now we'll look at the G structure, the Garrod structure. For this one, I'm going to get alternating phases. And so these will give us our pi G structures. Okay, so now we want to start constructing. We want to start constructing our possible molecular orbitals, knowing that somewhere in here we're going to have mixtures of SPs, SP2s, pi's, so on and so forth. Okay, so our first one is the easiest one. I'm just going to go ahead and draw C, just so we know this is what we're dealing with. And what we have here, this is our fully sigma G molecular orbital. Okay. Now, what we look at next is we're going to say, well, let me go back up and, oh goodness, do I have enough room to draw all these? Oh, I was supposed to draw these down here. Okay. Maybe this will help a little bit. There we go. There's our sigma G atomic orbital. Now, let's look at how that next one is formed. Does that look like we use the s orbital on the carbon?
Nope.
Nope, that's going to be where we use the sp on the carbon. And so what we'll have And let's see, we have a different phase. And then our carbon is going to have its sp orbital, making that sigma bond. So this one, our sigma U. Okay, let's take a look at this one. Now this one looks like we use the 2s on the carbon. And this will be where we use some of the sp2s from the oxygen. Okay. Okay, now how do you want to label this symmetry?
It's probably another sigma garage.
Yep,
right?
sigma G. Now these other two, these are very clear what these are.
Nice. Pi bonds.
Yep, pi bonds. Okay, so these are going to account for both of these possibilities. Okay, so even though, because you see here, the molecular orbitals are a very different reality than the schemes we come up with. Because here we know that those double bonds are, you see here where we have in and out of the plane and up and down in the represented. When in reality, we're getting this, when you just do the quantum mechanics, you get this overall pi structure of two degenerate structures that are going to go above and below and in and out of this. So again, it kind of shows the shortcomings of the scheme, but the scheme at least gives us an idea of what's occurring. And so, of course, this is going to be a mixture of p orbitals and a mixture of p orbitals with, of course, we know the oxygen is going to still have to have some hybridization to get its lone pairs. Each one's going to have to get its lone pairs as far away as possible. So we know that that's going to be mixed in there. This is just you just remember that so we can kind of explain it to us. And so this is going to be our pi u. Okay, now did I put that one? Oh, well, that's disappointing. With that one, pretty sure I put that one. No, I did. I just moved it energy wise. Okay. Now let's see. Second U. Yeah, I probably should have put that one up here, but we'll just do it here. Okay. So this one is going to be a mixture of sp2s and sps. So it looks a lot like this. And this is going to be another sigma U. Now, look at these two on the right. It's a horrible drawing, but you get the idea.
Sure.
So this one on the right. So you know that oxygen is going to hybridize in a way to get its lone pairs as far away from possible, but that's going to start leaving two p orbitals in there, and then one of the two p orbitals is going to form a pi bond this way, and one will form a pi bond this way, and that's going to leave partial p character going one way and then going the other. So it's you start to see how the actual quantum mechanics is like is more like a soup of all of these different approximations. So now we're getting this lone pair character, and so these are going to be non-bonding. Because first off, do you see how they don't reach all the way across? They don't touch the C. It's just localized on the oxygen. These are going to be non-bonding. These are going to be our lone pair characters.
Okay. So that'll just be those SP2s that are like.
Yeah, pretty much.
Okay.
This is going to be of Gouraud symmetry. And when we put this in the character table, the way it's most commonly put in, even though it's going to be non-bonding, I'm just going to call it in Gouraud. Some call it pi Gouraud, but it only has the one line drawn to it, so you know that it's a non-bonding stuck right there in the center. Okay, now we have our antibondings. Okay, so this one. Going to be that character. And so this is going to be pi star U. And then we have the same over here, just so there's that character. And then this one, of course, is sigma star. What do you think, Gouraud or Gouraud?
That's Gouraud.
And then this last one. This one's kind of hard to see because everything got smushed. But really what you have everything's facing the same way. So we have a sigma star Gouraud. You can kind of see how those various orbitals, when they repel, they smushed each other. All righty. So that was quite the construction. Now let's take a look at what this molecular orbital tree is going to look like. Okay, so we can go back up and we can see, well, this is definitely, this sigma G is definitely going to be our lowest. This sigma U has, you can see less electronic variation going on, so that's going to be next. And then this sigma G is going to be next. And now it can get a little confusing, but this is why it's nice to run the programs, because the next what we're going to have, I remember why I put it in that order, but I just forgot to change it back. So the next thing we're going to have, so then this sigma U is going to go next. So we'll start putting this together. We know that our these are going to go at the top, and so our pi stars are going to be lower in energy than our sigma stars, because of course those are more like side-to-side repulsion, where the sigma stars are head-on repulsion, and so there's a greater repulsive energy in the sigma stars. So all of these reasons, let's kind of see what we have here. Okay. Start there. Okay, so we're gonna have those sigma, that sigma G and sigma U we started with, okay? Now I'm gonna go ahead and write in that this one is, remember we talked about this? How we just, as we go up the tree, we just label these. So there are gonna be lower energy sigma G, so this is just the third one that we would come across if we did literally every orbital in the structure. But we're only worried about this frontier structure. And so then here, that's our 2 sigma U. Then we can start counting. We can do our count from there. Let's see, then up here, that's going to be our 4 sigma G that we talked about, which is right there. So we got sigma G, sigma U, then our 4 sigma G. And then the next one is, of course, that sigma U, which will be 3. Sigma U. Then we think about our pi structures. Okay, so I'm going to do one here. All right, and then do one there. And then I'm going to go up to the anti-bonding. Since I'm running out of room, these are closer than I like them to be, but you know, we'll get the idea. That's kind of centered. Oh boy. Okay, now, as we're looking, and in this middle structure, this non-bonding structure, I put 2 orbitals like a pi, because of course, so your oxygens are going to have multiple lone pairs. Okay, so you could either call this one, so okay, so you have your 1 pi U. So this one is either going to be 1 pi G or non-bonding G. Just depends on how you want to label it. And up here, 2 pi U. Now notice how we still counted that as 5 sigma G. So we keep that counting going even when we hit anti-bonding. And this will be our 4 U. Okay, so then what we want to try to take account of is all of our atomic orbitals. So the carbon, it is going to have a 2s, which is kind of right up here, close to the 4 sigma G. Then it's going to have its SP level. And it's going to have this level here. Because of course we remember that our hybrids are in between, energetically in between. Let's just go a little bit lower, kind of below that 1 pi. Is going to be, they're in between our S and our P orbitals energetically. All right, so this for the carbon. So this is carbon over here. That's our 2s orbital. These are our sp orbitals. And that's 2px and 2py. Okay. So on the other side, Alright, so slightly above the sigma. Now this might look a little weird. You notice how I'm putting two orbitals there, but this is two 2s and 2s, because remember we have oxygen and oxygen. Okay. So then we will go, where's this going to go? A little bit above 3. So we're going to go there. These are going to be our sp2 and sp2. And then, of course, this will go kind of in here a little bit above the non-bonding level. And this is our remaining 2p and 2p. All right, now let's kind of look at how these fit together. Okay, so our p orbitals are going to contribute to our pi's. Now, we know, first off, sp character has to give to non-bonding level because those non-bonding lone pairs are going to be on the oxygens. Okay. We also know our sp2s contribute to sigma bonding. Okay, but they're too high in energy to get those sigmas at the bottom, which is going to be a mix of these two s's. And the carbon, you'll see in that carbon sp should be slightly lower in energy, but anyway. You know, the carbon sp does actually contribute to the sigma bonding way down there. Oh, no, not that far down. Down to about there. And again, you could look this up, and if you a lot of, like, if you look at the textbook or something, instead of these sp2s, you're just going to see like 6 2p orbitals that will contribute to all this stuff. So it just depends on the source you look at. So then let's see, our p orbitals that contribute to pi structure. Okay. This sp is of course going to hit that sigma. Now, in all reality, they don't necessarily go that low. However, you could also make an argument. So I'm going to put that in there just because you could make that argument. And this 2s is going to go to that sigma. Now, of course, we want to join our antibodies. So pi character goes to the p levels, and then the sigma character. This is where you're going to go. That one's going to go to the higher one. This will actually contribute there, and there, and then this sp. Okay, on 2s. Actually go up to about there. So basically, I mean, the orbital structure gets complex. And so one of the reasons I'm saying you could make an argument to have a line here, a line there, is because you also have to keep in mind how many electrons each one of these is going to possibly have. It can't necessarily contribute more electrons. It can't contribute more electrons than it has, but then the argument is, where do those contributions actually go? But this is more or less the structure that you'd be looking at for carbon dioxide. And when we actually do the quantum mechanics, we come up with something like this. So of course there it's labeled as the 1 pi g, but again, that's from a structure where instead of putting in the hybrid orbitals, you actually are going to get, you're actually going to get,
High character.
your hybrid orbitals. So instead of putting in your hybrid orbitals, they're gonna on the diagram, they're gonna put in everything as a 2p for the oxygens. So it's just, again, it's a matter of argumentation. We're trying to calculate where things came from, where they go to, but in the end, what we really get is you calculate the orbitals and you get all of these molecular orbitals, and then of course they're all eigenvalues at given values of electron volts. So it's just you can get that center structure without really worrying about the size and what's going to be there, because as I said, you'll have all of these listed, lowest energy to highest energy, based off their allowed quantum states. So again, all of this is really just kind of a mechanism to try to explain what's really going on. But you notice that as we get more and more molecules, these structures get more and more complex.
Yeah.
Okay, that's pretty much the end of that chapter in a nutshell. There was a couple of molecules I left off, like they did sulfur hexafluoride, but they gave you a really good diagram for it, so you can see what that's going to end up looking like. But the whole idea of these multi-atomic molecules is we really want to start to understand the whole idea of ligand groups. In the end, there are more important things like understanding coordination chemistry, and then I can just calculate the quantum mechanics. Okay, so we're going to be starting into acids, bases, and ions and aqueous solutions. Again, a lot of this at the very beginning is going to seem very familiar to you, but this chapter does go much deeper into certain topics, and the chapter ends with our first look at coordination chemistry, which is going to be our next major topic for inorganic chemistry. This will feel, so as where the other chapters felt like quantum mechanics mostly, this is going to feel more like strict chemistry to you. Okay, so the properties of water. Water is self-ionizing. Depends on the textbook you look at. Some call this auto-ionization, some call it self-ionization. But it's, you basically have molecules of a pure liquid interacting with each other, and they ionize each other. In this case, you'll see various waters are going to pull a hydrogen or a proton off another water, and you're going to get these hydroxyl and hydronium species. And this is your, and it's called this is where I start having trouble with the pronunciations. Autoprotolysis.
Sounds right.
So we're going to start making sure, again, we're going to make sure we're expanding your vocabulary more as we go through this. But remember that we have an equilibrium constant for this, Kw, which is about 1.0 times 10 to the negative 14th. And do you remember what the brackets mean around
Concentration.
concentration? You've probably seen that a lot in organic chemistry.
Yep.
Okay, so water is a Bronsted acid or base. So Bronsted acids are proton donors. Bronsted bases are proton acceptors. And water, of course, first off, it's amphoteric. Do you remember? Look at these equations. What do you think amphoteric means?
Amphoteric?
Amphoteric.
That means that it has that's something to do with the polarity, right?
Nope.
No?
Look at what water's doing.
I'm thinking amphipathic, I think. Oh, it can be either.
Yeah. It can be either an acid or a base. And so if it's an acid or a base, it's really going to depend on the relative strength of the other species in solution. So here we see water with sulfuric acid. Well, the Ka for sulfuric acid, it's like, you can't even look it up. It just says big. Like when you look it up, you're just like, okay, it's way, way, way more larger than anything else. So in this case, water is going to be the proton acceptor. So it's going to be the Bronsted base. But down here in the ammonia solution, it's going to be the proton donor. And so let's kind of think about, well, we're see here a Ka to a Kb. We know those are equilibria for acid and base. But what would, I don't know, let's just try kind of compare the Ka of ammonia to the Ka of sulfuric acid. Do you remember how we do that? How do we relate Ka and Kb?
You had to use the KW, right?
How do I use it?
Oh gosh. I don't remember the equation.
Okay, so Ka times Kb equals Kw. So
Okay.
if I take Kb and divide through, that's in this case going to give me 1.0 and then the negative 14 over the Kb of ammonia, 1.77 times the negative fifth. What we're going to get is a Ka for ammonia of 5.65 times 10 to the negative 10. So Kas on this level are micro, like they're minute.
Yeah.
So you see something, if we compare these two Ka values, we can start to see, yeah, why water is going to be the base in one, the acid in the other. Because of course, with a Ka that low, ammonia is just not going to donate a proton. But you also see its Kb is orders of magnitude larger than its Ka, so it's much more likely to accept a proton. Sure. But as what a good dividing range is like 10 to the negative third, and so that's where you so 10 to the negative third and above is where you start getting your stronger acids all the way up to like positive values, which is very strong. Your 10 to the negative fifth is still going to be a weak base, but it's still quite a bit larger than any Ka value that ammonia could produce. So of course here, our sulfuric acid is a proton donor, water is proton acceptor. So do you remember these terms here, where conjugate base, conjugate acid? So the sulfuric acid produces the hydrogen sulfate ion, which is going to be the conjugate base of the sulfuric acid. And then, of course, the water produces it becomes the hydronium, which is the conjugate acid of the Bronsted base, which is water. And so, of course, if it was going backwards, your hydronium would be a weak proton donor. Now, keep in mind, well, it'd actually be a strong proton donor. But your hydrogen sulfate is going to be a weak proton acceptor. So usually your strong acids produce a weak conjugate, your strong bases produce a weak conjugate, and then vice versa. And so if we look down here, what do we think the conjugate pairs are for the ammonia reaction?
I mean, the ammonium and the ammonium are conjugates.
Yep.
And then the water and the hydronium. That's what that's called, right?
Mm-hmm. And so what we have is this is our acid. Conjugate base. And then we're going to have our base. Conjugate acid. Okay, so nice, easy way to end the day, but we'll just keep continuing to plug along at this chapter, because next you're going to see something you didn't see in Gen Chem, which is activity, and what that means to a solution.
Why is water amphoteric? It's just the Ka and the Kb are the same, right? Is it something?
No, that depends. So it's amphoteric just because based off the situation it's in, it can be both the acid or the base.
Sure.
It can either donate protons or accept protons depending on the situation it's in.
Yeah.
That's what makes it amphoteric.